In this chapter, we will start with a question. Which is more important in a bicycle road race? Is it the wheel weight or the wheel aerodynamics? Then we'll get into a very interesting topic called computational fluid dynamics, yaw angle in airplanes and bicycles, effective yaw angle, and then my concept of flying your bike. Wheels are complex, as you know, with complex patterns airflow. With fluid dynamics, hope nobody panics, I want to more knowledge bestow. Now we're going to look at some deep section carbon rims. Many of these will be familiar to some of you, and we want to see how the depth of the carbon can reduce aerodynamic drag. This is a family of zip carbon rims going from left to right. It's obvious that the depth of the rim increases, and so does its mass. For a time trial or a triathlon, aerodynamics is all important, so Zip did some wind tunnel testing, which was very revealing. The testing was done by Fabian Cancellara, one of the best time trialists in the world, and this was the testing protocol. He rode a steady speed of 30 miles per hour with a power of 300 watts over a distance of 40 kilometers and tested various wheels in the process. We'll make a little table here and compare various rims, the type of rim, the depth, the weight, and the time it took to complete the time trial. Here is the aluminum rim, a clincher, 20 millimeters deep, 425 grams, and that rim, with that rim, the baseline was established from which all the others are compared. Okay, here we go with the 303 clincher, 45 millimeters deep, 562 grams. It took 60 seconds less time to complete the time trial. With the 404 clincher, deeper at 58 millimeters, 578 grams, but still faster, 71 seconds from the timeline and 11 seconds faster than the shorter depth and less weight in the 303. Continuing this trend, here's the 808, 81 millimeters deep, 650 grams, but still faster. And then the last one, the 1080, also a clincher, 108 millimeters deep, 800 grams, almost twice the mass of the aluminum rim, but 1.5 minutes faster to complete the time trial. So we can make some important observations from this time trial testing that was done, and the big one is that the aerodynamic advantage of the deeper section rim is overwhelmingly more important than the weight disadvantage, because I get increasingly a nice streamlined flow around the rim, and that produces less drag, and it doesn't hurt that the spokes become shorter going from left to right. I've become a big fan of Envy rims. They're very high quality carbon fiber rims. Some examples in the 45 millimeter depth rim would be a 440 gram clincher, a 295 gram tubular. These are very sturdy rims. This wheel set on the right weighed in at a mere 1,100 grams, and it was made from Envy tubulars, DT Swiss 190 hubs, Sapim CX-ray spokes, and internal aluminum nipples. This is a picture of a Trek Speed concept bike with ALS D3 wheels, and it turns out that the aerodynamics of a bicycle wheel is really pretty complicated. It's complex because you have a rotating wheel which is spinning but also moving laterally, so there's a lot of very high math involved in studying this. Computational fluid dynamics is used extensively to study aerodynamics. CFD is a system of mathematical modeling, and it can be used to study subtle changes in contours. It involves very complex equations and powerful computers to solve them. But let's say I'm designing a wheel and I come up with 5 theoretical concepts of variants of the design, A, B, C, D, and E. Well, I can use CFD to model those and figure out which ones are the most promising. Let's say it's C and E look the best. Then I can make prototypes of C and E rather than all five, because prototypes is quite expensive, and so is taking them to the wind tunnel. Wheel stability in a bicycle is something that's obviously important. It turns out that aero is not necessarily the same thing as stable. We have to have both, and it's a design imperative to make sure that we do. We're going to look closely at 4 factors that bear on this topic. One is yaw angle, and then air currents that occur on the surface of the rim, what is known as vortex shedding, and stability at high speed. Yaw angle is easiest to understand with respect to an airplane. Let's say I'm flying from Chicago to New York, and that is a course that is due east at 90 degrees. And let's say my airplane speed with no headwind is 300 miles per hour. But I have this picture here. I have a headwind, and the headwind is coming from the northeast, which is 10 degrees to the left at, let's say, 50 miles an hour. I have to turn the airplane slightly to the left, which gives me a leftward yaw angle, and I accept the fact that my course velocity is going to be slower. You don't just add power to the airplane because that would reduce its efficiency. You accept the fact that you're going to have a longer flight. Here are a few graphics just to make the point. Flying from west to east in a no-wind condition, my airplane's heading is the same as its course, and it traverses the United States, in this case here, in 6 seconds. But if I have a slight headwind coming from the northeast, my airplane has to change its heading, and its course and heading will no longer be the same. And it will now look like this as it traverses the United States in now 7 seconds. This graphic here shows the same effect as worked out by Trek for yaw angle with a bicycle. Now what I'm going to do is try to break this down into pieces so we can see how this diagram is constructed. This is the direction of the rider motion. This vector is equal in length and opposite in direction to the rider motion, and it represents the airspeed of the rider in a no-wind condition. If the air is completely still and my rider is pedaling at a velocity of 20 miles per hour, his airspeed is 20 miles per hour. But now the situation changes and we have a quartering headwind coming from the left. The blue vector gives me the airspeed and direction of the wind. If I combine these two vectors like this, then I get the total airspeed. Then we have this yaw angle. Now we call that the effective yaw angle because we don't turn the bicycle to head into the wind like we would turn an airplane, because if we do, then we just ride off the road. And here's what I mean. Here's a different picture. We're showing somebody riding down the road here, and let's say we have a straight course and we're going 30 miles an hour with no wind, but we have a side wind coming from the right at, let's say, 20 miles per hour. We have to keep our heading straight, because if we turn to the right to head partly into the wind, we will just ride off the road. So what that results in, maybe a 25 mile an hour velocity going straight down the road with that side wind coming from the right. Here's what happens. I keep my wheels pointed straight down the road, because otherwise I will go off the road. But I have to lean to the right because that leaning is going to offset the wind. But the wheels want to now slide to the left, and I have to have increased friction to keep the tire on the road, and that increased friction results in a lower speed going straight.
Now we're going to look at yaw angle specifically as it applies to bicycle wheels.
I spent quite a bit of time making this graphic here, so just relax as I point out the components of this bicycle. The skewers, the frame, the hubs, the spokes, the handlebars with the orange bar tape, the cool green saddle, and the very aero deep section carbon rims. We're going to zero in on the rim and take a look at the effect of yaw angles. If this is our rim, we want to see what it means to have an effective yaw angle of 9 degrees compared to an effective yaw angle of 14 degrees. This is a graph from that same Trek white paper we saw a minute ago, and I'm going to walk you through this carefully because it's pretty easy to get lost. On the x-axis is the rider's velocity in miles per hour. So if the rider is pedaling at, let's say, 20 miles an hour in a no-wind condition, the only thing the rider feels in his face is an airspeed of 20 miles an hour. On the y-axis is the yaw angle, the effective yaw angle in degrees. Now, the curved lines here represent side wind speed. So, for example, the line down here represents 1 mile an hour of direct side wind speed. 2.5 miles an hour from the side, 5, 10, 15, and 20 miles an hour of direct side wind. In this diagram, side wind speed means directly from the side, 90 degrees directly from your left or from your right. But I'll show you in a minute how you can use this graph if you have a quartering side speed instead. Let's take an aerial view, and here's our bike moving to the right. That vector going to the right represents the direction of the rider's motion. In an equal and opposite direction is another vector that represents the rider's airspeed with no side wind. But now I have a side wind indicated by this vector showing the magnitude and direction. When I add these two vectors together, I get this one, which is the total apparent airspeed, and that angle is the effective yaw angle. Let's illustrate this with an example. Let's say we have 5 miles an hour of side wind speed. Let's start here with showing the rider going to the right at 20 miles an hour, which gives him an airspeed of 20 miles an hour in a no-wind condition. Here is my side wind speed of 5 miles an hour, and when I add these two vectors together, I get my apparent airspeed, and I have an effective yaw angle of 14 degrees. 14 degrees is the arctangent of 5 divided by 20. If I go to any online trig calculator and I type in 0.25, which is of course 5 divided by 20, and hit calculate, I get 14 degrees. I can get the exact same information from my graph. 20 miles an hour of rider velocity. I go up until I hit the 5 mile an hour line representing the side wind speed, go to the left, and I find that I have 14 degrees of effective yaw angle. At 20 miles per hour and a 5 mile an hour side wind, I have an effective yaw angle of 14 degrees. But if I'm riding at 30 miles an hour, then I go up to my 5 mile an hour of crosswind line and go to the left, and I have 9 degrees, which means that at 30 miles an hour in a 5 mile an hour side wind, I have an effective yaw angle of only 9 degrees. Here's my vector diagram for that same situation, rider at 30 miles an hour with the 5-mile-an-hour crosswind. Let's do one more. I'm riding along in a no wind condition, no side wind, 30 miles an hour, and I encounter a quartering side wind coming to me from the left at a 45-degree angle and a velocity of 7.1 miles per hour. Now that 7.1 miles per hour resolves into a vertical component of 5 miles an hour and a horizontal component of also 5 miles an hour. The rider's airspeed is now 35 miles an hour, 30 plus 5. But I still have to deal with my 5-mile-an-hour side wind component. That gives me this vector diagram with an effective yaw angle of 8.1 degrees. 8.1 degrees is the arctangent of 5 divided by 35. And I can likewise solve this from my graph by going from 35 miles an hour up to my 5-mile-an-hour crosswind line and over to the y-axis, and I get 8.1 degrees. Which means that as speed increases, the effective yaw angle decreases for a given side wind. High-performance rims are designed for faster riders, professionals for example, to achieve the best efficiency at yaw angles of plus or minus 15 degrees or less. We can actually use this discussion to help inform us on how to ride our bicycle, particularly in a race. So we're going to compare airplanes and bicycles according to several factors. Let's compare airplanes and bicycles with respect to power, energy capacity, side wind, and efficiency measurement. With an airplane, power is measured in engine thrust. In a bicycle, it's the number of watts put out by the rider. With respect to energy capacity, in an airplane, gallons of fuel. In a bicycle, dissolved glycogen and fat. Side wind, yaw angle, and effective yaw angle. And in terms of efficiency measurement, an airplane flies at a certain airspeed, but with a bicycle, we use watts as a way to measure our efficiency. I'll explain what I mean. In an airplane, flying at a certain airspeed gives us the best combination of fuel efficiency, range, and total time. On a bicycle, keeping track of my watts output gives me the best combination of consumption rate of glycogen and fat, endurance to complete a ride, and the total time. If I'm flying an airplane and I encounter some type of a headwind, either a direct headwind or a quartering headwind, I just accept the wind and continue to fly the same airspeed because adding more power will simply reduce my efficiency. The equivalence on a bicycle when you encounter the same situation would be to not increase your power, but to maintain your same power output because that is already what is going to give you the best efficiency in pedaling your bicycle, and you just accept the fact that you're going to go a little bit slower. So, fly your bike.